Greetings, my name is Andy Carter and I'm a professional engineer out of the state of Texas. In this video we're going to model a HEC-RAS bridge from scratch. Specifically, we're going to look at a bridge over the Navidad River on Interstate 10 midway between Houston and San Antonio. To follow along with this tutorial, 3 files are necessary. The first is a 3-foot resolution bare earth terrain model. It's a geotiff that was projected to the local South Central Texas U.S. Survey Foot projection. I provided a link to a tutorial to show you how this terrain was acquired. Second is a projection file that was created with QGIS that referenced this project's projection. Third, I'm providing as-built reference plans provided by the State Department of Transportation. If desired, download this project's data from this provided link. Let's start a new HEC-RAS project and import the project's terrain. With the Start menu, I'm just typing in HEC-RAS. I'm going to open HEC-RAS 5.0.7. Once this opens, I'm going to say File, New Project. This new project, I'm just going to put in the root of the C drive under RAS-Bridge. We'll call that Project Navidad, and we'll say OK. We're going to set it up in US unit, so we should be OK. We'll immediately go GIS Tools to RAS Mapper. We'll open RAS Mapper. First thing we're going to do is set the projection for the project. So under the Esri projection file, we're going to find that file that I previously created that is in South Central Texas U.S. Survey Feet. That's that .prj file. And we'll say Apply and OK. So now the project is set up in the right coordinate zone. Under Terrain, right-click and say Create a new RAS terrain. Hit the plus button. I'm going to navigate and go find that geotiff that was previously created for the site. And under that folder, I picked that folder icon. I like to name my surface something other than just what it defaults to. So I'm doing EG-LiDAR_3foot to say what resolution it was created in. Once we have all that, we'll hit create and everything will go off and process. This takes a few seconds to minutes depending on the size of the terrain file. I'm going to pause here for a second. And there we go. There's the site. The next step is to create a geometry file. We're going to do this inside of HEC-RAS Mapper. So back in HEC-RAS Mapper, I'm right-clicking on geometries and saying Add New Geometry Data. I'm just going to call this Existing and say OK. On the geometry, I'm going to right-click on Rivers and say Edit Geometry. Make sure that the pencil tool is selected. I'm going to zoom in and figure out where we're going to start the stream. I'm going to digitize that stream from upstream to downstream, down the Thalweg. Make sure it is upstream to downstream. It's very important. You can kind of notice I'm being a little rough here, but I'm roughly getting in the location of the creek in its appropriate location. You don't have to be super detailed, just depends on what kind of model you're building. Once that's done, I'm going to call that river Navidad, and the reach name I'm going to change to Main and say OK. So now with the edit session still active, we're going to right click on the cross sections, still having that pencil tool selected. I'm going to draw cross sections from left to right looking downstream. That's standard HEC-RAS nomenclature. I am trying to draw those cross sections to be perpendicular to the conveyance or the flow. Notice I'm skipping right over the bridge. We're going to come back and do the bridge a different way. Mainly I'm just trying to get a geometry file on which I can host the desired bridge. Once that's done, that edit session's done, just right click and say stop editing and say yes to save your edits. For this bridge modeling, we're going to export shapefiles and Google Earth aerials to assist with the modeling. Let's go back into RAS Mapper, and first let's export the river centerline. So I just right click on rivers and I say export shapefile. I'm going to name this as stream_ln just to denote it's a line shapefile, and that is the stream shapefile. Under cross sections, I right click on that, say export layer, and say save features as shapefile. And we're going to save this one to XS-LN for cross section lines, and we'll say save. So now we want to get some Google Earth aerials as well. So under map layers, we'll check that. We'll right click and say add web imagery layer. I'm going to go find Google Satellite and say OK. Since we've already specified a projection file, the aerial comes in the right place. I want a relatively low-res aerial of the road location, so I kind of zoom in to a point where I'm happy. I right-click on Google Satellite and say Export to TIFF. That's going to export a geotiff where it's going to have the correct projection embedded into it. This one's going to be GE-road for Google Earth Road. Now I'm zooming in to get a little bit of detail around the bridge itself that I'm trying to model. Specifically, I'm going to model the northern bridge. So I'm going to right click and say export to geotiff. We're going to put it in the same place, and we're going to call this one GE-bridge. And we'll say save and OK. Going to use Civil 3D to help manage the bridge modeling. So in Civil 3D, I need to make sure that that drawing is set up on the same projection. So right-clicking on the Settings tab, I'm going to set that drawing up under USA, Texas, and we're going to go find NAD 83, South Central Zone, US Survey Feet, and say Apply and OK. Now that I have that in, I can bring in those two geotiffs we created with a map image insert. I'm going to go find those two geotiffs, and we'll open them up. The low-res one, the bigger one, came on top of the high-res one, so I'm going to do a draw order and push the big one to the back so we can see the detailed bridge on top. Once that's done, now we can bring in the two shapefiles, and I'm going to do that as a map import. And I'm going to import the cross-section and the stream centerline and say OK, and OK again to bring those line work in. Using the aerial image as reference, we can now create the bridge and bounding cross-sections. Inside of Civil 3D, I'm going to draw a polyline down the center line of the road. This is going to represent the bridge deck. This line is left to right, looking downstream. Once that center line polyline is completed, offset it upstream and downstream 40 feet. These three lines all now are relatively the same length, which is important with bridge modeling. Inside of Civil 3D, I'm going to use the map export command, and we're going to export a shapefile that's all of the sections plus the three new ones. I'm going to browse to location where we had those files already exported. Call this new cross-section shapefile xs-ln_rev1 for revision 1. Use the line option, select manually, and pick all those cross-sections and export it out. Back inside of HEC-RAS, we're in RASMapper, and we're going to right-click and say Add New Geometry Data. This new geometry data is going to be called existing_rev1 for revision 1. We're going to right-click on it and say Edit. Go to the Rivers, right-click on it to Layer Properties, select the Features tab, bottom right Import Features, and then select the stream_ln for the streamline. This will come in and retain the name as previously done. We'll right-click on the cross-sections, go to Layer Properties, go to the Features tab, the Import Features button on the bottom right, and select the cross-sections revision 1 that we just created. This will recut and resample all the cross-sections, including the three new ones. Once that's completed, just right-click and save your edits to existing_revision 1. Back in HEC-RAS in general, we're just going to open the geometry editor. It's the third button from the left. And we're going to say File, Open Geometry Data, and select Existing Revision 1. This has those three new cross-sections which have been cut off of the terrain. Under Tools, go to Cross-Section Point Filter. Find the cross-section that's down the middle of the road. In this case, it's cross-section 1400. On the bottom, we're changing the horizontal filter tolerance and the vertical filter tolerance, etc. to 0.15. The last one, which is collinear minimum change in slope, will change to 0.060, and we'll filter the points. The goal is to create a bridge deck down the center line of the road. Right-click and say Graphical Cross-Section Edit. If you right-click, you can select Delete Objects. I'm going to delete all the points that represent points that are not indicative of the bridge deck. So we're effectively just trying to model the center line of the road itself. Now that I'm complete, I can say Exit Editor, and we can save the geometry file. We now have enough information to start modeling a bridge deck inside of HEC-RAS. Going back to the reference construction drawings, we'll note that the bridge is 41 foot 1.5 inch wide. Now we'll go into CAD and get the distance between the upstream bounding cross-section and the road deck, just drawing a simple polyline and querying it. And that tells me that the length is 22.6 feet. Both these numbers are important to model. Going back into HEC-RAS, we'll select the geometric editor. On the cross-section edit tool, I'm going to find cross-section 1400, which represents the road deck. I'm going to highlight all of the station and elevation data and copy it to the clipboard. Now that I have it, I can say Options, Delete Cross-Section, can remove cross-section 1400, close the cross-section editor, go to the bridge editor, and say Options, Add Bridge Culvert. I'm going to add one at 1400. We'll go to the Bridge Roadway Deck tool. The distance between the upstream bounding cross-section and the road deck was 22.6 feet as we figured it out. The width of the road deck is 41.125 per the plans. For station and high chord, I'm just Control-Ving the data on the clipboard. I'm hitting copy upstream to downstream, and we'll say OK, and we've got our bridge deck. Back on the construction drawings, we'll look at the bridge deck information to get the geometry that we need to model. I've highlighted the bridge deck in red. Everything that's pertinent for modeling I've highlighted in yellow. It's a 315-foot long span. It's composed of 6 40-foot girder spans and one I-beam span, which is 75 feet long. The elevation that starts the bridge is noted as a 296.13, and it's a 0% slope, so it's flat across. All the piers are 24-inch diameter piers at the 40-foot spans. We go to the next sheet, we'll notice that there's a 75-foot span, which is flanked by 30-inch diameter piers, and also has a little thicker bridge deck. And then we return back to the normal section, which is the girder section, and the piers change back to a 24-inch diameter. Looking at the sections, we'll note that the girder section is 36 inches from the top of pavement to the bottom of the bridge itself. This excludes the bents, and you'll notice here that the road deck and the I-beams on the longer span, this is the 75-foot span, is 51 inches thick from top of road to bottom of beam. Back in Civil 3D, I'm going to create an alignment from the road centerline. This is going to be used as station control to assist with modeling the other pertinent items of the bridge. I'm going to call that alignment bridge. Note that the station is left to right looking downstream. I'm going to draw a polyline. The first one's going to be at the abutment, the left abutment of the bridge. Then I'm going to offset that 40 feet. That's going to be to the termination of the first bridge span. We'll offset that one 40 feet, and this is the big span that goes over the main center line of the creek. We'll offset that 75 feet, and then we'll continue to offset 40 feet each until we get to the right abutment. I'm going to add a station offset label at the termination of each one of these polylines. This is going to assist with the high and low chord bridge modeling as well as the placement of the piers. Once I've labeled one station and offset, I can copy that style and just snap it to the endpoint of the other lines. I've created a brand new Excel file and entered in the stations for all points that were queried. As we noted from the construction plans, the high chord is 296.13 and it is flat and across the entire bridge, so we can just copy that all the way down. The low chord is going to be 36 inches below the high chord where we have a 40-foot span, so we can just assume for now that it's 293.13, and that low chord is all the way down. Now going back to where that 75-foot span is, we noted that it's actually 51 inches thick, and the difference between the high chord and the low chord minus 51 inches is 291.88, and that is at the first point and the second point. There's a couple things that we need to do to adjust these stations. I'm going to insert a row right before and one right after. So let's do this one at 440.12, and we'll do the last one at 755.14. What I'm trying to do here is I know that I have a high chord, and then the low chord is going to be 0. It's going to go as far down as it can go, and we'll do the same thing on this high chord. The other things that we're going to want to do is we want to insert a point right before we have the variance between the beam thickness. I'm going to insert and shift those cells down. We're going to insert and shift those cells down. So we're going to do one that is practically right next to that point, 0.12, and we'll do 595.14. We'll put the high chord as the same, and this high chord as the same, and the low chord we'll actually do with the 40-foot span. Back in HEC-RAS, we're now going to append the roadway deck data. We've found that bridge. We'll click on roadway deck. We'll just highlight and pick all those ordnance, Control-C them, and then we'll Control-V them back into Excel. We'll note that we now have everything between 440 and 755, so we will go ahead and delete the point that we have on the road deck already, and we'll just right click and say insert, and we'll insert those cells down, and we'll just copy these and we'll stick them in. So now we can come back and delete this to clean it up. And now we've got appended road deck data. We'll just copy and we will paste it into the road deck to overwrite it. And we'll make sure we'll click this button that says copy upstream to downstream, and we'll say OK. And there's our road geometry, our opening area. With the bridge deck in, now we can start modeling both the piers and the abutments. The next step is to add the piers. I've highlighted in Excel the location of the 6 piers that need to be modeled. On the bridge editor, I'm going to select the pier button, and we're going to add a pier at 480.13. That is for both the upstream and the downstream station. The pier width is going to be 2 feet or 24 inches per the reference construction plans. The first elevation will be at 0. The second elevation will be just above the low chord, so I'm going to set that at 293.5, and I'm going to select this button, copy upstream to down. Once one pier has been created, it can be copied to another location. I'm just going to copy pier 1. I'm going to change its station to 520.12. Both upstream and downstream will be at the same station. Its pier width is 30 inches, so we'll change the pier width to 2.5. And once we've done it for the upstream, I can just copy the upstream to the downstream and say OK. And there is our second pier. I've just completed modeling all of the piers. I've jumped ahead. Now I'm going to model the abutments. Note on the geometric editor you can pick a point and it will tell you the station and elevation of that given point. This helps with modeling the sloping abutments. The construction plans say that we have a 2-to-1 concrete abutment, so I'm going to go ahead and model that now. I'm starting at a 440.12 and an elevation of 293.13, and then I'm progressing 50 station feet to 490.12, and sloping down at 2-to-1 ends us at a 468.13. I will copy upstream to downstream and say OK, and there is our first abutment. Now I need to model the abutment on the other side, so back to the sloping abutment tool. I will say add, and we've got another one. So we'll start at a station of 700.14 at an elevation of 268.13, and we will end 50 feet at a 755.14, and we'll be 25 vertical feet higher at 293.13. We'll copy up to down as again and say OK, and there's our other sloping abutment. Now we're going to edit the ineffective flow areas on the upstream and downstream bounding cross sections for the bridge. HEC-RAS makes this easy as they give you a button on the bridge editor, so we'll go to 1440. And when you select that, it automatically defaults to the ineffective mode. The left station is going to be where the abutment started, which is 440.13. And we're going to do an elevation right below the high chord of the deck, which is going to be 296.13. And on the right, we're going to put that at a station at where the abutment ends, which is 755.14. And its elevation is going to be the same. When I model ineffective flow areas, I always check the permanent mode, specifically around the bridges, and say OK. Back on the bridge editor, now we're going to add ineffective flow areas to the downstream bounding cross section. We'll pick this 1360. That will go to the ineffective mode by default. We'll put it at the same stations, which is 440.13, and that's going to be an elevation of 296.13, and on the right side it is going to be a 555.14 at the same elevation, 296.13. Again, we'll set both modes to permanent and say OK. In addition to the upstream and downstream bounding cross sections, HEC-RAS has guidance that recommends that the cross section upstream and downstream of those two bounding cross sections also take into account ineffective flow areas. Coming from that abutment on the approach, it is recommended a 45-degree angle for where that ineffective conveyance is flowing. So I'm drawing a line perpendicular, and then I'm just rotating it negative 45 degrees on one side and 45 degrees on the other side. This is mimicking a 1-to-1 expansion of effective conveyance. We don't know the station as to where those 2 points hit on that cross section, so as before I'll say alignment, create alignment from objects. I'll pick that and we'll say that alignment we'll just call upstream, and we'll say OK. And picking that alignment contextually, the ribbon comes up and I'll just say station offset, and I'll pick a point here with 0 offset, and I'll do the same thing as the other side. We'll snap to that point, make sure we've got it, and enter. So those are the two stations where ineffective area begins for that upstream cross section. For this tutorial, we're going to ignore and pretend like we don't have a downstream bridge. To model the downstream ineffective expansion, we'll come off of that same point and we will go perpendicular to that cross section downstream. For the expansion, it's recommended as a 30 degree, which would be a 2-to-1, so we're going to rotate that 30 degrees. It takes a little longer for the water to expand back to its conveyance limits, and we'll do that again there, and I'll rotate this guy, in this case negative 30 degrees, and expand it out. Again, we'll just create an alignment from the object, which is that cross section. We'll hit enter, and we'll call that a DS for downstream. Having that, we can now pick the alignment, add a label, and we want to station and offset where that hits. We'll hit 0 for the station and offset. That's at 317.03 roughly, and the other one is going to be at 283.02. So we now have the limits of the contraction and expansion of the ineffective flow areas on the approach to the bridge. Going back over into HEC-RAS, specifically to the geometry editor, I've made a note as to where those limits are for those two cross sections. So we'll go to the cross section editor and we will go find that cross section. So the first one is 1657. So I'm going to go find 1657, and I'm going to say options, ineffective flow areas, and we're going to add it to the same station, which is 7. Let me move this down, which is going to be 275.16, and the second one is going to be at 997.99. I'm going to set those elevations to 296.13, which mimics the bridge deck downstream. We'll copy that over, set both of those as permanent, and we'll go to the next cross section, which is 1017, and we'll say options, add ineffective flow areas. We will set that at 317.27 and 983.02, and we will set those at the same elevation of 296.13. Copy that, make them both permanent, and say OK. Now we need to adjust the expansion and contraction coefficients for the two cross sections upstream and downstream of the bridge. This is to accommodate the loss of energy caused by the contraction of water as it approaches the bridge. We'll go to cross section editor and we'll go find cross section 1657. That's the most upstream. It's 2 upstream of the bridge. So let's go find that. You'll notice the expansion contraction coefficients typically default to 0.1 and 0.3. Around a bridge we change that to 0.3 and to 0.5 for the expansion. We do this for the 4 cross sections. So this one, the upstream bounding cross section changes to 0.3 and 0.5. The downstream bounding cross section changes to 0.3 and 0.5. And then finally that expanded cross section on the downstream side is 0.3 and 0.5. And we'll say apply, and we'll save the geometry. Now I'm going to quickly run a little bit of magic to get this HEC-RAS model to run. Under the geometry editor, I'm just going to go tables, Manning's ends. I'm going to select everything, set values to 0.060. That sets a Manning's end on every cross section. We'll say OK and file save geometry data. Now I need a flow file just to make it run, so I'm going to create a new flow file, and we'll just put a default 20,000 cubic feet per second. Reach boundary conditions, I'm going to set it at a normal depth of 0.005% or 0.5%. We'll save the flow data, and we'll just call it temp for kind of an existing one. We'll say OK, and we'll exit the flow data, and now we'll do a steady state plan, and I'll say file save plan as, we'll just call this temp, and we'll call it temp on the shorthand name and say OK, and just hit compute, and everything should execute. So now we can kind of go back to RAS Mapper and see what we did with the bridge that we modeled. This should give us some results. And there's our depth grid. Back in the main HEC-RAS window, we're going to click the Profile tool, and you'll notice that we've got the bridge, and you can see the backwater that's being caused and the acceleration as it goes through the bridge itself. Let's take a look at the cross sections, specifically the ones around the bridge if we can find them. There's the bridge upstream and the bridge downstream. And the two cross sections that are bounding relative to it, if you see this crosshatch, that means it's ineffective flow area, and while it's getting wet, it is not counted as computational conveyance. And this is one of those downstream cross sections as it expands back out. You can see that again we also have ineffective flow area where it's not flowing. To completion of this exercise, there was a lot of things that I had to change regarding Manning's ends and effective and expansion contraction areas. If you notice, I actually modeled two bridges for each bridge crossing, and there was an upstream and a downstream bridge. Let's look at that in profile and see what we've got. I've modeled a lot of profiles, so we're just going to pick one. And let's go back and just pick that 20,000 CFS like we did in the other model. So there are the two bridges that you can see. If we look at the cross sections, specifically around the bridge itself, there's the upstream and downstream bounding cross sections. I've actually got two bridge openings in this instance. And that's the first bridge. There's your expansion, contraction, your ineffective flow areas that are set. Same thing there. And it's just an expansion of what we just showed you. This concludes my introduction into bridge modeling with HEC-RAS. I appreciate the opportunity to show you what I do every day, and if you got any questions, please feel free to reach out to me. I appreciate your time.